Hi, Tim, how are you?
Very good. How about you?
I'm not good. So, what's going on? I had serious health issues recently.
Oh, I see, yeah.
So I'm sitting in my home instead of...
No, in my room, in my office, East Coast office.
So can you hear and see things okay?
Yes. Can you hear me?
Yes.
Okay, good. I'm sorry that because I misunderstand whose defense was held on Tuesday. Actually, it's Beijing's time Wednesday morning, so that conflicted with my course.
It's okay. Thank you. At least they picked it up before the defense started.
Given Hausa is your last student, do you still have other students at this moment?
I have two. I have Jose and Oscar Hart is sitting next to Jose.
I see.
Let me call
Or are we waiting on Professor Long? Is that who we're?
Yeah.
Okay. Yeah.
We'll call it.
Okay. Have you seen him wandering around today, Jose? Is he on the floor?
I saw him here today.
Can't get on through?
Yeah, he was in the meeting downstairs.
Good.
Okay, thank you. So I'll be there soon.
Okay.
I like your bow tie, Jose.
Thank you.
I don't think I'd seen you dressed up like that.
Just that way, like, soon after I came here, when he was treasurer or something of CSGFC.
Yes. I was a treasurer, I think.
I think we are waiting for another committee member, Sean Watt.
I knew him, yeah.
Also, if it's closed, people might think it's a closed.
Now thing is the head of your department, right?
And the head of the department, yes.
Oh, sorry, it's coming.
So,
Very sorry. Hey, Deepak, good to see you.
good, hi, Sean, thank you. Should we start? That's okay with everybody?
Yeah.
Yes.
Yes. Come.
Yes.
Well,
Okay.
welcome to Jose Abel Castellano Zoo's events. The committee members are Professor Nigel John from Peking University, Chen Moore from Wuhan University, Shuang Lan, our department chair here, and myself. My name is Deepak Kapoor. And Jose would have about 45 minutes to make a presentation. And before I let you start, I'd like to thank every meeting member as well as other participants here for being here at a somewhat odd time. For folks in Beijing, I think it's 9 o'clock in the morning or 10 o'clock?
8 o'clock.
Oh, sorry, sorry about that, 8 o'clock in the morning, and so it's 6 p.m. here. Now, you can start, unless you have any questions for the procedure. Basically, you can make a presentation, and I'm hoping that you will allow people to interrupt and ask questions, and after that, we'll have a full discussion.
Okay.
Please go ahead.
Thank you, Professor Kapoor. Can you, the remote audience, can hear me clearly, or should I move?
Yes. Yes.
Okay, good. So,
We
okay,
can hear you.
okay. Thank you everybody for coming to my defense, the audience here at the 3100 conference room, and the people attending virtually through Zoom. So my name is Jose Abel Castellanos Ho. I'm from Mexico, and I did a dissertation on a topic called computing certificates in quadratic modules, specifically on the univariate case, and one particular subcase in the for checking the inconsistency of a quadratic module in the multivariate case, generated by a single generator. Oh, 1 second. Okay, so this is our agenda for today. First, I will present some motivation, state clearly the problem that we are addressing in this thesis, some background about like some preliminary concepts that are heavily used, and some notation, and basic results in the existing literature. Then we will proceed with some main results about like list of contributions. Following that will be a section of key ideas, construction, and examples, where basically we're going to just pick the constructions related to the univariate case, discussing some key insights about like these algorithms, and finally we're going to conclude with some conclusions on future work. Okay, so for the motivation and problem, suppose we have these three polynomials. F is 1 minus x squared, and g1, g2, those display on the screen. So one question that we have is, how can we certify that f is a non-negative polynomial where these two polynomials g1 and g2 are both non-negative as well? So one easy way to do this is, of course, like compute some calculus, minimum values, and check that you are intersecting this set of solutions. But having this observation here that if you have two non-negative polynomials over some set, both their sum and their products are also non-negative over the same set. And another this case trivial observation is that the set of sum of squares are non-negative over R. With this observation, it's pretty easy to see that this linear combination of a sum of squares plus a sum of squares multiplying g1 and a sum of squares multiplying g2 is also non-negative over the solution set for these two polynomials g1 and g2. And furthermore, we can check algebraically that this f equals to this linear combination. So we can conclude that this property holds for this polynomial f. This particular representation, which has a name, is called a representation in the quadratic module. We're going to define a little bit later. It's pretty useful for checking that this non-negative solution, that one particular polynomial is non-negative over the solution set of this of a collection of polynomials. Why? Because all you have to do is check algebraically that the equality holds, and you know that the representation is given to you as the list of polynomials that, if you square them, will be these sum of squares multipliers. A fundamental question, or the main question that this thesis addresses, is that how can we find such representations in general when for any non-negative polynomial over any arbitrary set of polynomials. So just to show or illustrate that. To illustrate that this is not a straightforward problem, there are already some techniques in the literature that addresses this problem to some extent. The naive approach is to iterate this construction where you have fixed degree polynomials, some of us that you're going to square them, and then try to find the real coefficients of these polynomials such that the linear combination establishes the equality. But the problem with finding the real coefficients of this problem, of course, you can rearrange expressions and set a bunch of inequalities, is that one, usually solvers for solving polynomial equations might work over complex solutions, so that might not be of our own interest because we're looking for solutions with real coefficients. So for instance, if we set m and d both equals to 1, we obtain this set of these 5 equations. And there's no solution for this system of equations. So what does it mean? That we basically need to keep increasing these both m and d, until we find a solution. And also it's not that clear upfront that something is, just by being a non-negative polynomial, there will be a representation like this. There is, of course, a representation of this polynomial, because we mentioned that at the beginning. However, interestingly enough, if we provide partial solutions to the previous corresponding system of equations in the settings m equals to 2 and d equals to 1, Mathematica, for instance, this computer algebra software struggles to find the real solutions to this problem. If we provide like 6 partial solutions, it's pretty straightforward. It finds the solution. But if we start removing hints to this system of equations, the system starts to struggle until it's not even capable of finding within a reasonable time solutions for this using this particular approach. Another approach that is also in the literature is something called the extended grand matrix method. The question? Okay. The extended grand matrix method relies on using semi-definite programming. The approach there is to find semi-definite positive matrices such that they find the sum of square representation. One key fact, or one particular property, one fact of this within this theory is that a sum of squares, a polynomial is a sum of squares. It admits such a particular representation if and only if there exists if there exists semi-definite positive matrices such that f equals to b transpose times a times b, where b is some vector of monomials. As we said, this approach uses semi-definite programming to find these certificates, but one of the drawbacks of this approach is that the SDP solvers are numerical methods, and usually they rely, or the implementations that are available use interior point methods, where are numerical approximations. So the kinds of answers that we get out of this approach are usually not exact. So just to illustrate this example, this example illustrates the construction of the grand matrix. This polynomial, 1 minus x plus x squared minus x cubed plus x to the fourth, might not look like, but actually that is a non-negative polynomial. And in fact, in the univariate case, all the non-negative polynomials are sums of squares. We can see that because of the existence of this semi-definite positive matrix, A, and we can check this equality, F admits a sum of squares decomposition. In fact, one of the sum of squares decomposition for F is this expression. One way to obtain this particular expression is by working with the Chomsky decomposition of A. So you will obtain these two matrices, and basically the representation here will be the coefficients of the row vectors, because by following the previous definition, matrix A having this form basically will form a dot product between this matrix and the monomial of vectors. Now, in the problem that we mentioned at the beginning, using this extended grand matrix method, we obtain these numerical matrices in 3 because we need 3 sums of squares. Oh, sorry, I did a mistake. I pressed a button that. Sorry, I ended up going to the end. Sorry about this. Okay, going back. I'm here. Yes. So this, okay, in the extended grand matrix method, we obtain these matrices, and we can see that by expanding the result, we'll still can obtain a sum of square representation of the certificates. However, the error terms in the numerical solver introduces this extra term that is not exactly the same original polynomial f, which was 1 minus x squared. We actually will go back to this example because we're going to discuss this in one of the upcoming in the next slides. So we will explain what we do for this and our method to obtain these sum of squares using our approach. Just to mention a little bit more about this this problem in the existing literature, there are different approaches. One is the constructive real algebraic geometry. Mostly results about this are coming from Lombardi. The authors claim that their system is complete. Unfortunately, the complexity level of their algorithms is a 5-tower exponential complexity result, which seems to be, everybody will agree that is impractical for any practical application. However, that is complete and is constructive, exact and constructive. The second related piece of literature is some lines of research involving finding bounds that measure the complexity degree of these certificates. Usually authors in this area will be Schweighofer, Nijie, where they mention bounds for for obtaining the degrees of these certificates in terms of the degrees of the input polynomials, the generators, as well as some metric distances between the smallest root of f with respect to the set of generators. Some other results involve the membership checking using valuation theory, which is a particular branch in model theory interested in solving problems in algebra that usually just led to the proving the desirability of these problems, either by using valuation theory, which is just an approach that try to use extended real closed fields in order to obtain the results. And also another popular technique in the literature is using certificates with hybrid methods. Hybrid methods are a combination between the symbolic and numeric approaches, where first the numeric approach is being used, and then there is an effort to do some rationalization of these floating point approximation answers in order to obtain an exact solution. So moving to background, during this presentation and in the thesis, we usually work with the set of real algebraic numbers, because in general, having a polynomial with real coefficients is practically an undecidable problem. So we restrict ourselves to be most of the time actually rational numbers. But for context, I mentioned here real algebraic numbers, because we're going to use them later. Given a polynomial, f of c denotes the real zeros of f. This symbol here, the summation of the ring square, is going to denote the sum of squares. The sums of squares with algebraic coefficients. Given some set of generators G1 to Gs, we denote by Sg. The solution set in the literature is called the semi-algebraic set. In this case, this is particularly something called a basic semi-algebraic set, because it's the solution to a conjunction of polynomial inequalities. Finally, if there's any subset of the real numbers, in multiple dimensions, the pos of S basically denotes the polynomials that are non-negative over this collection of this subset S of Rn. Now we're going to start with some technical definitions, but the representation that we were working at the beginning has a proper name called the quadratic module representation. A quadratic module is an algebraic structure that is closed under addition, closed under multiplication by squares, sums of squares in the ambient ring, and contains the constant one. Given a set of polynomials, the set the quadratic module generated by G, abbreviated QMG, is this collection of polynomials. A priori is a more general concept that also allows the algebraic structure to be closed under multiplications. So basically, the set of the a priori generated by some particular set of generators is going to be of this form. It's just a product of all these generators. Finally, because the thesis focuses on the Archimedean case, a a quadratic module is called Archimedean if the quadratic module contains the polynomial n minus the sum of all the variables. But because we're going to be focusing in this presentation on the univariate case, the quadratic module is Archimedean if it contains the polynomial n minus x squared, where n is a positive constant. So to the state or problem, we referred to this sum of squares in the previous definition, the sigmas, as the certificate. So the goal for the certificate problem in quadratic modules is that given that we know a member in the quadratic module, the goal is to find the sum of squares multipliers such that this equality holds. We usually refer to the polynomial f as the input polynomial. And yeah, as mentioned before, this thesis concerns on the computational aspects of this problem in the Archimedean quadratic module in one variable. So the main ingredients that the thesis uses are basically this collection of results. The first one is a fundamental result by Augustine. During her, for her Ph.D. thesis, she provided a decision procedure to check if a polynomial is a member of a given quadratic module, Archimedean quadratic module, or not. She relies on making concrete, tractable use of result in the evaluation theory of the local global principle of Jacobi. We're going to talk about it a little bit later. Also, I rely on the algorithm provided by Shah et al. This particular body, this work provides an algorithm that finds a certificate for strictly positive polynomials. Thirdly, they're like a collection of two papers. There's one after the other by the authors Marshall et al. So the first one, I think I forgot to pass. So, yeah, I just mentioned this. So the first one introduces a concept called the natural generators, which we're going to use in the first case of the case, in the first case that we handle in this thesis, which is the saturated case, and also a result that was heavily used during the thesis is the basic lemma, introducing the second version of this paper by Marshall, that only provides an interesting result, but also it provides a constructive proof of it. Let's see, yeah. So talking about the membership check, these are just two. These two ideas are that in order to check the membership, we usually rely on a data structure that uses two pieces of information: the order and the epsilon sign. The order is basically related to the multiplicity of a root in a given polynomial. It's easily, we can even prove that this order is related to the minimal natural number such that the nth derivative evaluated at that point is different to 0. The epsilon sign is defined as if this coefficient happens to be positive, it's going to be 1, and and otherwise it's going to be -1. And this data structure that I call, that I think is well known in the literature as the signature. These three functions keep track of relevant information about the membership properties of these polynomials. So this kappa plus, kappa minus are just keeping track of, in some sense, the even and the odds orders that has negative and positive or negative epsilon signs respectively. So this is the first result that was taken from the literature, the various membership check. As you can see, it's a result that basically states that membership holds if and only if the input polynomial is non-negative over the semi-algebraic set, and these three conditions apply. That for, in particular, basically the summary of this, in order for not to spend too much time on this, basically we just need to see at the endpoints of the intervals, because semi-algebraic sets in the univariate case are just collection of intervals. The particular observation from Farris is that we just need to pay attention to the endpoints of these intervals and keep track of these signature conditions that we mentioned before, in order to decide whether f a given polynomial is a member or not. As we mentioned before, we rely on the certificate algorithm. The name of the algorithm is certificate, so that's why the name certificate. It relies on an extension of a semi-constructive result by Abercoff. Abercoff proved some particular relationship between the non-negativity between polynomials and how we can lift the positivity of a polynomial to another set. So this particular construction was used because in the algorithm that I'm using has a specialized version for the generated case. First, just computes one single, reduces the problem to a monogenic problem, one single generator, and then uses two extensions of the Abercoff lemma to compute certificates for this expression. Natural generators, well, maybe these are explained in the thesis, but just to give a refresher or a quick description, is that for a set of intervals, you can have natural generators. By the sense of the word natural means that the least complex polynomials that are either linear or quadratic. So by having a collection of linear polynomials that are encoding to cut basically hyperplanes on this on the line, you can form intervals, and basically these are the ones that are going to be used for encoding the endpoints of the intervals that that are the semi-algebraic sets for one particular case, that is the saturated case. I want to, it's still describing the background, but the basic lemma, this is a fundamental cornerstone result using the thesis, basically says that if two polynomials f and g are non-negative over some semi-algebraic set of G and relatively prime, there exists strictly positive polynomials sigma and tau such that there is some Bezold-like identity where 1 equals to sigma times f plus tau times G. And in particular, if we restrict this set G to just be the product of f and G, then we can also lift this strictly positive polynomial sigma and tau to be sums of squares. This is a flowchart diagram explanation of the basic lemma that has been implemented and used in the Maple programming language. Basically, because we know that f and g are co-prime, there exists two polynomials s and t such that there's this Bezold identity. And then basically the rest of the algorithm are just two steps that keep making modifications to this s and t such that the sigma and tau become strictly positive. In order to achieve such conditions, basically the algorithm needs to enforce these two green boxes, which in some sense is really the hard part of the algorithm, to find the sigmas and the n, the sigma and the k. This is a high-level description of this basic lemma. And then, just before getting into the main results, we're going to say the assumptions that we make through this thesis. We assume that the input polynomials, both the input polynomial and the set of generators, are going to have rational coefficients in order to avoid decidability issues, and we have a representation for the machine. We also assume that the real roots of these polynomials are obtainable. There's literature, I think this book by Basu Roy, that explain algorithms to compute these particular to root isolate these roots, and also the sign conditions of the evaluation of the polynomial at these algebraic points is decidable. So what do I mean by the checking the evaluation of the sign condition? It's just like by plugging the number into the polynomial, we can check if it's negative 0 or positive. More notation. This is something that we abuse or use a lot during the thesis. We use something called lifting. The idea there is that we work on this is also like the idea is from linear algebra. If you want to go from one basis to the other, it's just enough to multiply a matrix So basically, if you want to go from one particular representation in some quadratic module, but you have certificates of each of these generators in another set, we just lift them. But the term is heavily used, and it's just this algebraic this algebraic identity. Also, we notice that this is encodable using matrix multiplications as coming from linear algebra. Okay. From the main results, the thesis addresses 3 cases. In order like to, well, technically 2, in order like to address the general problem. So the first case is called the saturated case. Oh, sorry. Sorry, I forgot. Well, first I will mention the contributions. The contributions are, the thesis introduces a technique called compactification. Compactification is a procedure that basically alleviates a restriction of the basic lemma. The basic lemma stated at the beginning mentions that the polynomial f and g, the semi-algebraic, the SOS variant, the semi-algebraic set of the product f and g is bounded. What happens if that product is not bounded? So compactification aims to take one particular element, in the quadratic module, and then finds a multiplier such that the resulting polynomial becomes bounded. So this computes another element h such that in the quadratic module such that the semi-algebraic set of h is bounded. H has the same series of f, and they also share the same order and same conditions. We solve the certificate problem for the saturated case. We're going to define what that is. What is that? Surely, but just like, yeah, maybe I should define what it is. Identify redundancies of the generator and the input polynomial using the monogenic, the information from the monogenic case. And finally solve the general certificate problem by combining the, I'm still talking about the monogenic case here, by combining the basic lemma and removing some roots of even multiplicities. We also introduced these 2 concepts, pure mixed polynomials, because they are going to be useful for solving the general problem. These 2 ideas basically keep track whether something actually is just enough to use a monogenic problem. And if not, basically they compose the problem into multiple monogenic problems and then combine them by making the by obtaining a product of these intermediate results, and then using the basic lemma to filter the desired result. For the latter, we need to introduce also an intermediate set of generators HFG that has the property that the certificates of the product of the members are computable, and and also solve the general problem in the Archimedean quadratic module that is symbolic and exact. And this is also a result from the thesis, but we're not going to discuss it in this presentation. Is to certify the membership of -1 for a multivariate generator, multivariate quadratic module. So the key ideas and construction examples. So what is the compactification? As I said, I think is straightforward. One of the shortcomings of the basic lemma is that FG, this semi-algebraic set, needs to be bounded. But if it's not, what do? We cannot use this variant. So basically, compactification aims to ensure that we can use this variant of the basic lemma by making sure that this product is going to be bounded. Because if it's not bounded, we find H such that will make it bounded. This method, in some sense, actually resembles the same construction of the basic lemma, because it can be seen as the basic lemma being applied on f, epsilon minus f, where for some epsilon that is greater, that is positive, that is related to the maximum values of f, and the set of generators of g. So yes, this is some notation. I think I'm going to skip this because I think I have already explained this before. We distinguish 3 cases when S is unbounded to the right, to the left, or both sizes. What do I mean by to the right? That it goes to infinity, positive to infinity to the right, and negative infinity to the left. The left case is the dual, is basically the opposite. And both sizes means that the polynomial f increases both to infinity to the left and to the right. I'm just going to discuss one of these cases. in some sense, it's actually pretty similar between the three. The only difference is that the right is, we just need to keep track of one single real root. For when you have to deal with both in both directions, there will be two roots. For the left case, basically we use an inversion. No, sir, it's a involution. By involution, I mean it's just a reflective map that maps x to minus x, and we're gonna basically go from the left case to the right case. So what is the construction here? There are two cases. If if the polynomial f of degree n happens to have n real different roots, there is a result in algebraic geometry called the Gauss-Lucas theorem that says that all the roots of all the derivatives will be within within the interval R1 Rn. So the Cauchy bound of f will be useful for processing that case. Otherwise, we're going to process the Cauchy bound of the derivative of f. The reason for that is because we want to avoid having to deal with the minimums of f to become positive. So we apply this construction, and then provides the desired solution for the compactification. One particular example is, suppose.
Can I ask a quick question?
Sure.
We go back to that slide real quick.
Sorry, 1 second.
That's all right. Sorry to interrupt. I just thought maybe I'd ask just to make sure
Okay.
I'm
This one?
kind of keeping track. Oh, up to the end again.
Yeah.
Sorry. You were around 23, 28.
Mm-hmm.
I was wondering about the else case. When you said that polynomial had those roots, I didn't quite understand what the else case meant. If it doesn't have those roots, and I apologize, this is a very simplistic kind of question. So you have, if f has R1 through Rn as roots, then you have something going on. You got the Cauchy bound.
Mm-hmm.
So, this is really a conceptual question. What's the else cover then? Does that mean that you just don't have n roots, or you don't have any roots? I kind of lost the plot there a little bit.
So you know that a polynomial can have a real root or can be complex, right? So if it's complex, basically you're not going to add up to n.
Okay, I see. I see. So basically it's going to have all n real roots.
Yes.
So not all real.
So the first case is that if you know that all the roots are real, and then they are different, by the way, because it's also a different, you can put them in a line, right? Then the Cauchy bound of f is enough to deal with this problem because of the result from Gauss-Lucas. On the other hand, if this is not guaranteed, you need to make sure that you do not make essentially epsilon minus f to become a non-negative polynomial over the semi-algebraic set of G.
Also, if I can say, the x case corresponds to when we have roots of multiplicity greater than 1. Same root multiple times occurring.
Gotcha. So part of the else there is the fact that they're not distinct.
That's right.
Is what you're saying.
That's
what Jose was also trying to say. Okay.
Yes, and also the Gauss-Lucas states this particular condition. So in order for me to use Gauss-Lucas and use the Cauchy bound of f, I need to ensure, basically also bring the hypothesis from that statement.
Sure, I understand.
And otherwise, if in some sense it's just an optimization. If that condition is valid, you can use Gauss-Lucas, and otherwise you just go and do the Cauchy bound of the derivative. Thank you, Rojas, for the question. Is that?
For interrupting.
No worries. No, thank you very much. Does that address your question?
It does. Yeah.
Okay.
Thank you.
So let us keep moving. This is an example. So in this case, what we want to do is compactify f. The semi-algebraic set of G is just one single interval minus 1 to 1. Semi-algebraic set of f is unbounded to the right because it's minus 2 to 2, and then 3 unbounded to the infinity. Following the algorithm, we compute the Cauchy bound, which is 20. We do the optimizations. We obtain the sum of squares multiplying this, and then that means that H is minus x minus 20, which is strictly positive over this algebraic set of minus 1 to 1. Why? Because this polynomial is, the algebraic set of this H is minus infinity to 20. Finally, we're moving to a serious certificate problem. The first case is the saturated case. Intuitively, the saturated case is it contains all the non-negative polynomials. I will say that this is actually the more useful result, because usually we're interested in checking the non-negativity. I mean, I'm not saying that the other results are not as useful as this one, but they also focus on the non-negative sense. But this is more, in some sense, is more efficient because you don't need to keep track of too much of the signature conditions. Because of there's an equivalence in the literature that explains that the orders will be just equivalent all to 1 at the endpoints, so you don't have to pay too much attention to this structure. Our approach, this is in one single paragraph what we do, lift the certificate of a priori that uses the natural generators, computes the certificates of the natural generators in the real set of generators, and then lift this certificate from the pre-ordering to the quadratic modules in the natural case, and then moving that representation again to the original set of generators. So this is an example. Right away, I'm just going to compute the certificate of the natural generators to skip some steps. We want to compute the product of these two natural generators. In order to lift basically the certificate from the pre-ordering to QM, basically we need to compute the product of the natural generators, but in the thesis we explain how we do this. And then to obtain a certificate in the quadratic modules, we have to use this basic lemma construction. Because we noticed that the natural generators also share some common roots with the real generators. We just use the basic lemma with these different inputs, the natural generator and the polynomial that has the natural generator as a factor, but we divided by that in order to have this particular Bezout identity. By multiplying the natural generator again to the whole equation, we obtain a certificate from here. We obtain the certificate of the natural generator in terms of the quadratic module. We do the same for the other natural generator, and then we lift, obtaining this certificate. I believe this is the result that we obtained at the beginning of this discussion during the motivation. Alternative approaches. So in the literature, even though the non-negative case has not been addressed quite extensively as the strictly positive case, there are methods that provide a solution to this problem. So this is another example. I'm not going to go into details, but the purpose of this slide is just to compare them. Our approach will find something like this. There is another existing approach by Zhang, where it is involved using a procedure called fixing. There are some pros and cons, of course, for each method. I will say that one condition in the Zhang's approach is that in order to ensure that there's some cancellations, I think it's needed to use to avoid modifying the order of the transformations. Finally, if we use this extended grand matrix approach, which is pretty efficient but numerical and non-exact, we'll obtain something like this. An experimental comparison of this. We have a benchmark that uses an implementation of the certificate problem for the saturated case. Also with Real Certify and this package, moment polynomial OPT. Real Certify is a package in Maple developed by a French group that obtains certificates of strictly positive polynomials. And moment polynomial OPT is a Julia package developed by a group in France. The main author is Italian. So both have their unique features, but on the other hand, I think there are some limitations as well. Both work for these two packages work for the multivariate case. However, if I use them for my problem in the univariate case, I also see some interesting observations. For example, here we compute the certificate of the natural generator added by 1 in order to make it strictly positive over some collection of polynomials. We see that our implementation is able to find all these certificates and in a reasonable time, whereas the real certified package struggles from 6 onwards, and moment polynomial OPT could not find the last one. The degrees obtained by all the packages are pretty similar, so we kind of have a sense that we are optimal in terms of the degree, but we haven't proved that yet. And this is another experimental comparison. Basically, in some sense, it's a dual, but the results are kind of similar. Now we move to the second major case in the thesis. Question, yes.
On the previous slides. So all of the tools they are using floating point numbers, floating point coefficients.
All of who?
All of these methods are using the floating point numbers for the coefficients. Or some of them are using rational numbers. Because you showed us one example using rational numbers.
Yes, okay, so actually these two packages, the real certifying and moment polynomial OTP, I haven't discussed how they approach the problem. They use a hybrid method. They combine the numerical power of the SDP, but also they rationalize the floating point numbers in order to make an exact representation. So all of them at the end obtain exact certificates. Sometimes when they cannot, because there are some conditions for this rationalization that they need to satisfy some geometrical conditions. Of course, they will just give you the floating point number. In this case, I think they all find, for this particular example I have in my thesis, I think I also compared output-wise the results. All of them obtain rational exact certificates. But I'm sure that for other more complicated problems where these geometrical conditions are not satisfied, the rationalization or the make it exact process is not feasible.
Okay.
Mm-hmm.
Not feasible means that the problem is not decidable.
I would say that in order to make it exact, so the technical term is a projection. So you have a point in this semi-definite space. You have a point that approximates some interior set of solutions. You can project to a rational point, right? And then in order for that condition to be met, you need to satisfy this geometrical condition that you still need to remain in the interior point. If you're not in the interior point of this set of solutions, it's not that easy to rationalize. So I think the solver would just give you the floating point representation.
Okay.
So let me interrupt. You have only, you're running out of time. You have another, I'll give you another 10 minutes. So please try to finish.
Yes, I will be more prompt, succinct. Okay, so in the next section we have the monogenic case. This is just generated by a single polynomial. The approach basically is a separation of concerns, tries to simplify the input polynomial in a way that separates the strictly positive part, separates something called the in-between factors, and only remains a polynomial that is divisible by the generator. And then in such case, in the last case, basically, we use the SOS variant in order to compute the certificate. For the other two cases, the in-between has a particular construction in the thesis. I'm not going to explain too much in this presentation, but of course the strictly positive part is handled by the certificate algorithm by Shang. We can combine easily all these certificates in these previous steps, because in the monogenic case, there is a particular feature that if you do the product of two certificates in the monogenic case, quite easily you could reach a representation in the monogenic case by just distributing the sum of squares in these representations. I'm going to be quick. This is one particular example. In some sense, this problem ended up, what is this? Boiling down to a strictly positive case. We use the certificate problem to obtain the certificate. So multiplying back the even terms in this term basically obtain the desired result. We have some experimental comparisons of a partial implementation of this. In this case, we use this monogenic problem, this set of products. this has a particular condition that the semi-algebraic set consists of a bunch of isolated points, are just minus n to minus n plus 1, minus n plus 2, up to n. And then we compute the certificate of the left generalized natural generator, something that I haven't mentioned, but it's a generalization of, of the natural generators. Oh my God. And another intermediate generalized natural generator. The results are, in this case, I just compare our approach with Chang's method, because both the real certifying and the moment of polynomial OPT, they both fail, because these are proper non-negative polynomial certificate problems. The others are supposed to handle strictly positive polynomials. So we notice that there is a slight advantage on the degree of these certificates that we obtain. There is not too much advantage, but in some sense also the quite interesting Chang's method is a little bit quicker. And the same basically for this table. Finally, for the general univariate case, I will attempt to explain succinctly what we do in this situation. There are multiple concepts that are needed, but I will hurry up. First, we introduce, we extend the simplification procedure from the monogenic case to handle multiple polynomials using the signature data structure. We introduce the following concepts: matching, pseudo-matching, and pair matching. I will briefly mention why all here is useful. As we mentioned before, we distinguish between pure and mixed polynomials using these particular two constructions, local relative gens and relative gens. I will explain in detail what these are, what are these, and the intermediate set of generators HFG, which have this property, as I mentioned before, that the certificate of their products is computable. So this is the technical definition of matches, pseudo-matches, and pair matches. But in some sense, what I'm trying to capture here is, conditions of the membership test by Farris. So matching, in some sense, is basically saying that both the input polynomial and another generator are congruent modulo the multiplicity, the order of the polynomial at a given point. Pseudo-matching captures strictly positive conditions, as well as that if this is another condition in the there is in Augustine's membership check, and pair matching is basically another condition in, by Augustine's membership procedure, where basically in order to define one particular point, you need to have two generators for a given point. These are just the intuition behind these definitions. Moving to the distinction with the pure and the mixed polynomials. As the word indicates, pure, in some sense, basically the idea there is that we can detect that the input polynomial is just basically generated by one single pure generator, one single polynomial. That reduces the problem to a monogenic problem. But if there are multiple, generators needed for each of the roots of f, then we need to mix by having different generators. These two concepts basically are keeping track of that. Yes. Yeah, because the motivation here is we distinguish the two cases. If f is just generated by a single polynomial, we use the compactification of such generator, because in such case this is properly a monogenic problem. Is this polynomial here will be bounded. On the other hand, if it's not, then we break the problem into multiple monogenic problems. All of them are compactified if needed, in order to guarantee that they are monogenic problems, monogenic certificate problems. Finally, I would just explain high level what is this HFG doing. Is an intermediate set of generators that need to keep track of these two properties in order to make sure that we can simplify the input polynomial, meaning that if we get rid of the strictly positive part of f, we can still use this intermediate set of generators to compute the certificate of the strictly positive polynomial. And the second condition allowed us to work with the factor of the input polynomial. That's basically the intuition of this. So again, maybe for this, I'm just going to skip some steps. But in here, I wanted to compute the certificate of F in terms of G1 and G2. The HGF is this. In the thesis, we describe the certificates of each of these polynomials in QMG in terms of QMG. The certificate of this is just technical details, but basically we apply this construction of the product and the basic lemma in order to obtain the certificates. Sometimes if we're lucky to have sums of squares, we don't have to do anything else, but if not, then we have to use the certificate algorithm to compute the strictly positive part of this. This is a really, I'm sorry for this slide, but this is a really convoluted output, but we are able to obtain these certificates. And finally, we just lift from this HFG to the original G by lifting or taking each intermediate generator into the original set of generators. Conclusions and future work. Well, we can conclude that this thesis obtains a fully symbolic and exact solution, does not rely on numerical methods, and can be implemented in computer algebra systems. We started this study of the general case by breaking down into two subcases, the saturated case and the monogenic case. And as I said, yes, I think these methods are novel, symbolic, and they obtain certificates in terms of the original set of generators and do not modify the set of generators by adding additional polynomials, which is usually the case in the existing literature that add Archimedean polynomials in case they become complicated. For future work, one of the observations is that the basic lemma, it is in the existing implementation is for the univariate case, but the original result is for the multivariate case. I think it will be interesting to see one particular specialization of this into the univariate case. Hopefully with that, we can get a better complexity result and we can speed up the results of the certificates that we obtain. Also, the certificate problem in SHA, which is applicable for the multivariate case, we need to, well, it will be ideal to have just a particular version for the univariate case in order to speed up the results. This is, and also, yeah, well, this is maybe not, well, let me see what it, and finally, we need to have complexity results of this polynomial, of these algorithms. Currently, there are no complexity analysis of this. Most of the reason for that is, well, there is some technical level of difficulty. In fact, for even simpler cases of just single intervals, complexity results involve a lot of metrics that if something becomes really close to this algebraic set, the degrees can increase indefinitely. So we need more time and efforts on obtaining complexity analysis of this. Thank you very much for your attention, and I will be happy to take questions.
Thank you very much, Jose. We appreciate sticking to the time schedule. We'll start with questions from the committee. Let's start with Nigel Young.
Hi, Jose. I have several questions regarding your thesis. The first question is about the complexity of your algorithm. You need to answer my question one by one, or just after all my questions?
We're going to do all the questions and then we'll answer them. Then we can go one by one. First, you go do all the questions to them.
So you are suggesting, sorry, could you repeat the suggestion?
Nigel, we're going to ask all the questions together, and then you take one by one.
Okay.
Okay. So my first question is regarding the complexity of your approach. The second question you see that in your approach you use the compactification to make unbounded problem to bounded one. Actually, you see that there is a very standard technique just developed in the optimization community. You see that you can use some of the homogenization technique. You just by introduce some additional variable, then you can map unbounded problem to bounded problem. That could be useful in your approach. Maybe it just some suggestion. Maybe you don't need to answer this question.
Okay.
That is very helpful. Yeah.
Mm-hmm.
And my last question is about you say you mentioned using some result you mentioned in the literature possibly to extend the univariate case to multivariate case. Do you can talk about more? Particularly you mentioned this in your future work. Maybe could you talk about more in details?
Yes.
That's my most three questions.
Thank you. Go ahead.
I think I forgot. I need to have
First
this.
question has to do with the complexity of the algorithm.
Okay, thank you very much for keeping track of this. Yeah, the complexity analysis. So the complexity analysis of algorithms is not addressed in the thesis. In order to spend some, I think, in order to spend some time doing that, basically I think there are some conditions. I think the bottleneck is mostly on the. What is this? On the bottleneck is mostly on the nature of the problem. So as you can see in the community, when they want to do some scientific computation, what is this? They usually resort to approximate solutions, and then, for instance, I think one example is the Newton-Raphson algorithm. To some approximation, they can say how much they need to iterate. But in this case, I think it's kind of complicated because on the one hand, we are asking for exact solutions, and at the same time, we're dealing with real numbers. So I think one of these problems should be studied. I think, I think like the complexity problems of the algorithm needs to be addressed. But I think the existing literature addresses some of these complexity results. I think, in particular, Real Certify provides some bounds. So probably, I think some time needs to be spent to address these problems.
Let's go to the second comment that Nigel has, which he says that instead of compactification, he says there's a standard technique in symbolic computation of homogenization.
Yes, okay.
Polynomial which is unbounded.
Yeah, homogenization.
And make it bounded.
Yes.
Before we do that, can I interject related to this other question? Do the empirical results tell us anything about the relative complexity of Jose's approach compared to what's already in the literature?
No, but in some sense I cannot make a conclusion out of the complexity results or the bounds. Why? Because, well, in particular, that's the reason why we did some experimental results in the thesis, because of the lack of this complexity analysis. We wanted to provide some meaningful measure that at least the system is not providing some insane or arbitrarily large values for these degrees. So by testing all the implementations, we sort of get a conclusion that at least the implementation seems to be going in the right way. But of course, complexity results need to be addressed.
Third question Nigel had was,
So,
what can you say about the problems related to multivariate quadratic module? But we have to be very brief now, because you can spend hours here. Go ahead.
sorry, can I address the homogenization problem? Or
No, let's go to the third one, because that is its comment, that's okay.
Okay. I see. Okay, that's okay. Moving to the third point, which was the multivariate case. Okay, so for the multivariate case, this problem is, even though it's in the univariate case, ended up posing a challenge. The reason for that is because not only I approached this directly, I approached the non-negative case, which is in some sense hard, because if you're non-negative, you're touching the endpoints of the intervals. If you were to believe, but it's not quite right, Stengler's complexity analysis, you will think that the certificates for such polynomials should be infinity, but that is not also what Stengler is saying. In any case, it presumes some difficulty. Now, moving to the multivariate case, there should be some literature because in fairness, my work for the thesis was to make some existing theorems and constructive results in algebra and the algebraic geometry to become algorithms. So existing results in the multivariate case, I think, are related to Marshall, but also they impose conditions like the Hessian of the set of generators. They should have certain properties, and I think no one has addressed these problems because, okay, another of the issues is that quite conveniently in the univariate case, all the non-negative polynomials are sums of squares. But when you jump from to two variables, sums of squares, non-negative polynomials are not automatically sums of squares because of this famous Hilbert's result. So basically, my constructions of really obtaining non-negative polynomials that you can express them as sums of squares, they need way more effort. Current approaches I think people are doing to address the multivariate cases to relax the definition of sums of squares and allow to have non-negative polynomials over multiple variables in order to facilitate or keep going with some sort of representation, but following this, I mean, not necessarily having quadratic modules, but something that helps in the verification of the non-negativity.
Any further questions?
Yes, I got the question. Actually, you see that if you have some further suggestion, you say that in your introduction part you mentioned the library. You say actually the membership problem, even for the multivariate, can be still handled by using that the library means that you just define some template, then you can reduce how to synthesize the parameters of the templates by reducing to some semi-definite problem or so. Once your approach, the complexity of your approach is too high, for example, double differential or so, actually you can try using the library. Actually, you see that the semi-definite problem can be solved using the symbolic computation way. Actually, definitely, in practice, the practical viewpoint is the complexity is too high. Few people use that technique. But theoretically speaking, it can be solved by in that way.
Yes.
Even in the symbolic way, yeah. That's my comment.
Okay. To address the comment, if I understand correctly, you're proposing that the SDP approach can be useful for even solving the certificate problem in the multivariate case. I do agree with your statement. However, I think there are some caveats, right? Because usually there could be some numerical problems that would lead you to believe that there is something that is a member, where it's not. And then when you do the rationalization and try to exploit or use these geometrical constraints, you will not get a representation. In fact, I'm not that experienced with real certify, but looking through the traces of the software, sometimes they report that they have found a solution, but they have to backtrack because it's not actually something that satisfies some geometrical constraints, or they see that some eigenvalue is negative, or it is not definitely a semi-definite programming. So I would say that your approach is useful and actually practical to approximate members in the quadratic module. However, for even deciding the membership, the Archimedeanness of a multivariate polynomial, deciding the Archimedeanness of a multivariate quadratic module is decidable, but there is no algorithm for that. So, yeah, I think there should be a trade-off, and the approach of the SDP definitely can help, again, verifying the non-negativity. And yeah.
Anything else, Nigel?
Yes, yeah.
That's it? Any other?
Yeah, that's it. Yeah.
Okay.
That
Thank
was
you.
my questions. Yeah. Thank you.
Professor Chen Jingbo.
Yes, can you hear me?
Yes.
Okay, Jose, thank you for the presentation. I have 3 questions. The first 2 is concerned with your 2 essential ingredients you used in the thesis. The first is the natural generators. So why do you use the natural generators? And so what are the underlying benefits to work with these generators instead of the original ones? Okay. The second question is about the basic lemma. Can you go back to the slides or
Yes.
the presentation of basic lemma?
Yeah, I'm writing an. There was this slide. No, sorry.
Yeah, at the beginning.
This one?
Yeah, this one.
Okay.
Yeah. So I'm trying to understand this from the viewpoint of polynomial equations. So when you have two co-prime polynomials, then you can find say the coefficient like sigma and tau here, like this equation holds. And in the polynomial equation case, this equation can be used to find the inverse of m modulo j. Is your use of basic lemma for handling quadratic modular have some similarity for this? Like you are trying to find the inverse of one polynomial f modular the other. Is this any similarity? This is my second question. The third question is about the other softwares. You mentioned in your presentation that for real Certifying and the other software package end with opt, okay, there are some cases they cannot handle. Can you summarize some of these cases and explain why they fail and your method has succeeded?
Okay.
Yes, that's my three questions.
Yes. So I go to the first one. Let me see. The natural universe. Well, the reason why we use the natural universe. Yeah, that will be helpful. Okay. So why we use natural universe is because in the saturated case, the algorithm is as follows. Find a certificate of a member in the preordering. First, actually, let me say something more, a fact. In the univariate case, preorderings and quadratic modules match in the sense that if you have a preordering, there exists a quadratic module representation. They're not the same representations, but in the univariate case, they're the same. Why? Because quadratic modules in the univariate case are close on their products. Now, why do we use natural universe? Is because there is this result from Agustin that she finds a certificate of any non-negative polynomial using a certificate in the preordering. Or goal in the saturated case is to lift the certificate in the preordering structure to jump from the preordering of the natural universe to the quadratic modules generated by the natural universe, and then lift the quadratic module generated by the natural universe to the quadratic module of the original set of polynomials. Why we didn't do directly the certificate in the original set of polynomials? I mean, I'm addressing the question of what did I did the thing, but I'm not saying the alternative. Well, from the top of my head, I will say that the technical issue, let me see. Yeah, okay.
I can help you a little bit. I think the natural generators set is basically has a very nice input structure, which is being dictated by the internal semi-algebraic set.
Yes.
And because of that, you can get representation easily, and then you can compute the product that's natural representation also. Otherwise, using the original basis, you will be have to compute again the product computations in fashion. If I'm wrong,
no, that is precisely the reason. I think the reason why the intermediate step was to use the set of natural universe is because algorithmically you can find the certificate of the product of natural universe. On the other hand, finding certificates of products of generators is harder. So working.
Okay, I'm good with this.
Yes. About the basic lemma, right? I don't remember the details of the question, but if I rephrase, you mentioned something about like if we have a Bezoar identity, we can have a solution module one of these polynomials. In some sense, yes, because as we have seen during some examples, by manipulating this identity 1 equals to this linear combination, we can find the certificate for either F or G in terms of the product of these two, right? But I do not understand the question. Could you repeat again this?
Yes, so we can use this identity in the polynomial equation case to find the inverse of F modular G. Okay, do you use this identity in the same way or in a similar way?
Yeah, I will say so. Why? Because the manipulation. Okay, the manipulation. Yeah, the manipulation of this identity again. If from this you could obtain certificates for F, G, or the product, because if you do what is this? Yeah, if you just multiply both sizes by either F, G, or the product, you obtain something that is in terms of F, G, or the product. Now, something that is more interesting. Sorry?
Okay, I get the idea.
Okay. And the third question about the real certified and monomial OTP. So the literature on those papers seems relatively complete. I will say myself, why personally, that maybe the results from them are complete. The problem with the real certified and monomial, the other package, is that their implementation. So there could be some bugs or incompleteness in the implementation. I have some communication with the authors. Sometimes they acknowledge there is a mistake and they will fix it. But there is indeed, what is this? What they have agreed on is that their software relies on having at least one generator that is bounded. Because otherwise, I mean, they technically mention that as the ball condition, because the ball is just something that resembles the Archimedean polynomial. So I think there is something in the encoding that relies on having such a polynomial. If this polynomial, that is the semi-algebraic set of this polynomial, that is bounded, is missing, they struggle from a that is the best I could say without saying something wrong, I guess.
Are you okay with it, Jung-Chi?
Then I think the other part of my question is that why your method can succeed.
Oh, yes. So in the success stories is because in the thesis we also consider the non-negativity condition. Usually the design of these two packages and the theories are they entirely focus on the strictly positive case. Of course, the strictly positive, they need to include the zeros in order to become non-negative at these endpoints, or in the multivariate case at the corners of these surfaces. But I will say that because intentionally the thesis addresses or takes into consideration non-negative polynomials, that is the reason why we happen to obtain certificates for a little bit more of these polynomials.
Okay, thank you.
Thank you, Professor Kinch.
Okay, that's all my questions.
Okay. Sean, please.
Hi, so Jose, my question is going to be much easier because I really, I'm not very comfortable with all these things. But for myself, right, I was just curious with this slides, right, what does it really mean when we say two polynomials are relatively prime? And how do you find the coefficients of sigma and r? Is that a variation of the Euclidean algorithm for the Bezoar identity?
Yes. So first question, what does it mean to be a relatively prime?
Right.
So
Yeah.
two polynomials, or in algebra, two objects are relatively prime if there exist two polynomials ST such that the linear combination, this one, 1 minus 1 equals S times F plus T times G. Another way to see that is that in algebra using Grobner basis, there's no common solution between these two polynomials, right? So there is well-known characterizations of what does relatively primeness mean. In the context that we're using, we do, care about these two polynomials S and T. Of course, how do we find this S and T? How do I undo? Well, okay, sorry. How do we find this is, you can iterate the Euclidean division, so you can divide F divides G, and vice versa. You have a sequence of residues you could, until you see, you could start doing this process of dividing S over G. And then if there's a residue, you divide now the residue over the previous other polynomial. You repeat until you get to 1. There's a termination condition because there are no common zeros. So if you carefully track of these expressions and then rewrite them backwards, I think you obtain this identity. So that is how the identity is obtained. I don't know if you had another question or was.
No, I think the real challenge here is we have to just have polynomials, the multipliers have to be greater than or equal to 0 on the S of G, not on the whole ring.
Yes.
Is that right?
Yes. So I think
That's the lower part of the picture you have.
So the question, if I remember, was how actually sigma and tau become strictly positive? Well, if that is so these conditions here, we can do an analysis if we see what is sigma. Sigma is ST, but what is S1? Sorry, S1. S1 is this polynomial S plus NG. So basically we have S plus N minus R, which R happens to be this equation. The key feature here is an identity that says something like 1 minus C times the summation of from the geometric powers of 1 minus C equals 1 minus CK. It's just a geometric telescopic series, right? Well, with that particular fact, you can start rewriting these expressions, and then it takes some time, but what is this? Because of all these conditions are guaranteed, what is this? You conclude that these resulting expressions are strictly positive.
Okay, so Deepak, you're muted. So,
Any more questions, Ron?
you guys have one good question. So Jose, what is your plan after this?
Right away, after graduation, you mean? I will be applying for postdocs. I think I have some discussions and opportunities, but we're still, yeah.
Great. Thank you, the committee. Now we're going to go to the audience. I will reserve my question at the end.
Or the
So, any questions from the audience, please?
yeah.
I have a question. So I'm just guessing. I don't know. Oh, they have a microphone.
Can you say
No,
your name?
because the microphone is from the computer.
Oh.
But I can repeat the question.
Oh yeah. So I'm just a guess. I don't know too much about this, but your abstract mentions there are applications to like robotics. So could you give maybe a few examples of how this could be applied to applied fields?
Yes. So the question by John, thank you, John, for the question, is that in the abstract, because we circulated an announcement here at the CS department, there was an abstract that I mentioned that there are applications of these results into other applied fields, and these applied fields could be robotics, something like that, right? The question from John is, mention one concrete application out of this. So I was looking into this. So there is in control conditions that are of interest, like stability, divergence. So I think if you have a dynamical system, you're interested in checking that something is going to be within some space, right? Or it's not going to get outside, what is this, some region of interest, because that could be interpreted as a crash or something like that. So basically, like checking the non-negativity of this, I think, called Lyapunov, I don't know the pronunciation, maybe I'm butchering the name, Lyapunov conditions. I think you can easily test the safety, stability of these dynamical systems. So I think robotics is a field where you actually use work. I haven't worked in robotics, but based on what I have read, people work on these models, and you could check the safety of the system by checking these particular properties.
Thank you.
Thank you.
Any other questions?
Also from Zoom, I think there's quite people.
Yeah, from Zoom, any questions from Zoom?
Raise your hand if I.
It doesn't look like, give the committee again a chance to ask any additional questions that they may have. Okay, doesn't look right. So let me ask you my question, or there's a question. No, there's a, let me ask, my question was when you came here to UNM, you knew a little bit of logic, maybe more logic, but you didn't hardly knew any algebra. So all this stuff that you presented is pretty sophisticated algebra and math. How did you learn all this?
I would say that my savior was really access to computer algebra systems, because indeed my approach towards all this is probably unintuitive, and I leverage too much on software doing the dirty work for me. In that sense, by that I mean that probably I'm a little bit lazy working out all these expressions, and if Mathematica says that it's empty, or if there is no other better way to write down a polynomial, I think that's my approach. I usually work really with the computer. With such a tool, basically, I was able to verify this, and in some sense, basically, I just thought that when we discussed this problem, it was interesting. We noticed how hard it was. We ended up making simplifications, and we ended up agreeing on the univariate case to some extent. I thought generally that I had a chance to find a solution for this problem, honestly, because I thought that it was so I mean, the univariate case, you cannot even go any simpler than that. And with the time, I also realized that it is not really like a a solution, how to say this? I mean, it's a novel solution. It is not a solution in the sense of being like the first solution, because of course, if you use one of these decision methods, you can work out your way using semi-definite programming and trickery to rationalize stuff in order to find the solutions. But what I thought that I just had a chance to have this problem because I thought, because what drags me was also like when I was working with examples and was obtaining certificates, to me I was quite amazed that even though the theory says that they exist, I'm still in disbelief when I see a certificate, because it's like a really complicated object to find. But when you see it, it's like, yes, that is a sum of squares. It's easy to see that is true, but it's pretty hard to obtain. Yes.
So next question is, if somebody wants to continue this work, some student or postdoc, what advice will you give to them? You haven't thought about it? That's okay.
Yeah, I haven't thought about it, but I will say, I mean, from the top of my head, focus on what matters, and try to make efforts into what is this? I mean, because this is this is an advice in the negative sense of what not to do, because I also remember that I was quite inefficient and I was avoiding, I was wasting too much time by trying to learn all the things that were surrounding this area that were not actually useful for the algorithms. And there is a lot of results in model theory. There is a bunch of areas that are really interesting to know. But in order to make progress, really one has to focus on the things that matter and making sure that progress is done by having discussions on this. Yeah. So I think just focus on particular sub-goals and making sure that progress is done in that way. I think that would be my advice.
Thank you very much. Thank you, Ms. Tanko, for the presentation. And after that, I think the committee will discuss, have a discussion.
Okay. Thank you. Thank you, everybody, for.
Jose, how do I make this discussion private?
1 second. Yeah. So I will give you full access. Thank you. So I'm not sure if the audience is coming back, but in case I don't see you guys, thank you very much for attending to my defense. It means a lot to me, your support. So I will give Professor Kapoor ownership of this room, so I'm out. So see you guys.
Can you throw people out?
Yeah, I will. I will kick them out. Sorry, guys.
Maybe Diva, you can put Jose in the waiting room.
No, I think that so make co-host. So I think Professor Kapoor has ownership of this. So thank you everybody for coming. All the audience. Thank you. So okay. So I will get out. Thank you. Bye bye.
I'm sorry you have to leave.
Yes.
Yes. Jose, I think Deepak asked you to kick out all the other participants online before you leave. Yes, they could by themselves.
Yeah, so I will remove. They could have left the computer there and then like.
Yes. Okay, so see you later.
Good. Thank you. Thank you very much.
So Jose, you need to leave.
Yeah, I also need to leave.
You will be kicked out too.
Okay. Thank you, guys. So the guy who thank you very much for your